Hi guys, welcome to another video on macOS internals. In this video, we'll talk about dynamic memory allocation, more precisely, how to trace allocated blocks and how to find memory leaks. We'll also look under the hood to understand why and how leaks can be identified. Let's start with a simple example. As we'll see in a moment, the body of the main function is very short. Take a moment to study the code. There's a loop which calls another function whose name is self-explanatory, doLeaks. Inside this second function, I've added a memory allocation instruction. I'm using malloc and the 256 bytes block size, but notice there is no corresponding call to free the allocated memory block. Not good, because basically this function will create a small leak every time it's called. The code is straightforward. At the end, we have a getChar call that will allow wait for input. This will pause the application before exiting and allow us to see what happened with the memory blocks. First, let's compile our little program and take a peek under the hood by watching the memory allocations. A very useful flag related to memory allocation that we can pass to the allocator in an environment variable is malloc stack logging. This will record all the memory allocations done while running the application. After that, we can use a tool like malloc history. Let's use the second terminal. Malloc history. We need to provide as parameter the process name or the process ID, a PID. And then let's list all allocations ordered by size. There are other possible flags. Feel free to play with the tool. Very interesting. We even have the allocations coming from system libraries. If we scroll just for a bit further, we should see the allocations coming from our application. Okay, so we know how to check the application's allocations. Let's next see the memory leaks. We will use the built-in tool called leaks. No surprise. Again, we can either provide the process name or a process PID and -list flag. Because we started with the malloc stack logging environment flag set, we again see almost the same information as before. But notice here that we have 3 memory leaks. Each of them is 256 bytes. 3 leaks, exactly as in the code. What about applications already started? The good thing is that we don't even need to start the application with that flag. We will still get very meaningful results. Let's see. We don't see anymore the allocations from the system libraries. But we do get all our 3 memory leaks, which is what we're after. Great! Let's next use the debugger and understand what's happening behind the scene. Enter LLDB, set up 2 breakpoints in our 2 functions. First in the main function and then in the doLeak function. We can also use the shortest syntax, just B for breakpoint. Then run the application. It will stop in the main function. If we continue, we'll stop next in the doLeak function. And here we see the call to malloc. Let's advance to the next instructions. This is the call to malloc. Execute it. The result is a memory block whose address is stored in the RIX register. This is the address ending in B20. At this point, there is no memory leak and we're still inside the doLeak function. let's advance to the next instruction. The RIT instruction will exit the function, and we can check the leaks again. What do you think? Since we've exited the function, do we have a leak now or not? Pause the video for a minute and think about it. Alright, let's check if we have a leak or not. No leaks. 0 memory leaks reported. What do you think there is a leak? Remember, we actually exited the function. There is no way for us to deallocate that block. It's lost. Actually, not quite. If we go back a few screens, there is a possible way to deallocate that block. This is because the address of the block was stored into the RIX register after the call to malloc. So this is the address of the block ending in 5B20. And at this point, the RAX register still contains that same address of the memory block. Notice that the next instruction actually overrides EAX. After that instruction, there's definitely no way for the application to know about the memory block. If we check the leaks, as expected, we should see the first leak. Allow the application to continue execution. In the end, we have all 3 memory leaks here. Before wrapping up this episode, let's see another useful flag that we can pass to leaks application. It will allow us to output a memory graph, possibly very useful. Start our leaky application and, the same as before, but just pass the output graph parameter. This should generate a memory graph that we could use with tools like malloc history, for example. Instead of passing a process name, we'll provide a memory graph. Notice that because we didn't use the malloc stack logging flag, we cannot get meaningful information just yet. So let's do it again with the flag set. Start the leaky application. Then dump the memory graph and finally load the memory graph to be read by malloc history. Exactly as before, we have all the memory allocations, the ones coming from the system libraries, and also the allocations coming from our code, and the leaks as well. We've seen before the 3 calls to allocate 668 bytes. These are the ones we performed, and so on. To wrap up, in this part, we've seen how to trace dynamic memory allocations. We've seen how to identify memory leaks and also performed low-level debugging to understand what it means to create a memory leak and how they are identified. I hope you'll put this information to good use. Make your applications as clean as possible without leaks. Thank you very much and see you in the next episodes. Cheers!